recording. So welcome. So this is chapter 10, which is projectile and satellite motion. And I suppose the first thing I should say is that what is projectile motion? And projectile motion is when an object is only pulled by the force of gravity. So there's no air resistance, there's no cannon pushing, there's no rocket engines, there's no propellers, you can't have any of that. So a really good example of a projectile would be a cannonball, or maybe a football that's been thrown. Not so good, because the air resistance becomes more obvious, is a golf ball. Golf balls have little dimples in, and they're designed to aerodynamically affect the ball, so they kind of cheat, if you like. And if you kick a beach balls are classic. They go really strong and then they fade as the air resistance gets them, because they're so light. And in fact, just in my life, in looking at soccer, when I played soccer when I was a kid, there was a big, heavy leather football, and it was covered in mud because we lived in a wet, rainy country. And by the end of the game, it would be, it would be massive. You'd kick it with all your strength, and it would go next to no distance. And you go to professional games, and they were stronger and faster, but they also had these same limits. And then I came to the States, and I didn't watch soccer for years. And then one World Cup, I got interested again, and I watched it. And they could kick the ball, with some power, half the football field. And then I noticed that the ball would curve tremendously. And then I started talking to my brother, and he goes, oh, yeah, they made the balls much lighter, and they make them in a way so that they do curve. And what that means is that you get to a situation where, for the goalie, it's really hard because the ball is moving around, drifting one way or another. Projectiles don't do that. So we've got this very idealized case. So, okay, we can picture that. Satellites. So things in space get a little bit misleading, because the most common misconception is that people think there's no gravity. They're in space, so there's no gravity. And it turns out they're only about 100 miles above the surface of the Earth. If you're in the space shuttle, you're only about 100 miles above the surface of the Earth. It's like from here to Orlando upwards. It's not that far. And when you compare it with the 4,000 miles from the middle of the Earth to here, 4,000 versus 4,100 is next to no difference. So the people in the space station have pretty much the same amount of gravity that we have. It's a little bit less, but it's not significantly less. It's measurable, but it's not like amazingly significant. But what's happening is they are falling all the time. It's like stepping off a cliff and never landing. And as you know, if you've ever stepped off a cliff, is if you're holding something and you step off a cliff and you let go of it, it stays in front of you because it's falling. Well, if you're falling and it's falling side by side, it just stays there whether you're touching it or not. And from your perspective, it might look like it's floating because it's not moving down or moving up, it's just there. So when you see these videos from the space station and they basically, spin pens in the air, because there is air in the space station, they spin pens and they float around. It's not that there's no gravity. It's that they're falling and the space station's falling. So it's a very strange situation. That confuses us, which is interesting. So has anybody here done any skydiving? Occasionally there's somebody who's done skydiving. So when you jump out of an aeroplane, your stomach kind of goes into the roof of your mouth, yeah? Is that horrible feeling?
Yeah, actually not. It's not like a roller coaster where... Oh. Yeah, that's what I thought. It'd be that feeling.
But you don't feel that immediate kind of...
No, it's more like sticking your head out like a car window.
That's once you've kind of like got to some speed, yeah?
I guess so, yeah.
But when
I remember like feeling that stomach up in your throat feeling.
Okay.
More of just like...
Yes.
You can't tell you're falling because
yes.
It's discontinuous.
So let me, from a physics, having never done it, let me talk about it, okay? So from a physics point of view, Once you reach terminal velocity, then you're not speeding up. And so there's effectively no acceleration. So it feels like you put your head out of the window of a car. It's like that. It's that feeling. You're not falling. But what surprises me a little bit is when you first jump out of the aeroplane, it is like jumping off a wall. And there is that I would have imagined. I've never done it.
Just like fear probably trumps that.
Okay, yeah. The adrenaline or whatever.
Yeah, you don't really, I don't remember feeling that.
That feeling.
Or just like, what did I just do?
Okay. Now, that feeling, and it's not probably as extreme as a roller coaster ride, because a roller coaster ride is made to make you feel the acceleration tremendously. But it is a 1G kind of like, acceleration. And the astronauts feel that all the time. And that's the kind of weird thing. They're falling all the time. And so they have to do training. If you went up into space and just were in the space station, you would feel that uneasiness all the time. And what the experience shows is people vomit if they do it for too long. So they put them on a thing called a vomit comet, which is a plane that simulates that, we'll call it weightlessness. It's not gravitylessness, it's weightlessness. And it simulates it, and they do all of them together, so there might be 4 hours of this rocking, and your experiment might only take 20 minutes. So you do your experiment, and then you sit there for 3 hours and 40 minutes while other people are doing stuff, and you vomit. And they actually put the astronauts up there to just get them used to it so that they can withhold that. So that's very interesting. So how many times have you done the...
Just once.
Oh, just once. So
Expensive.
there must have been, adrenaline must have been going like crazy.
It was.
Was
yeah.
it tandem or were you by
It
yourself?
was, yeah. Yeah, you can go by yourself, you just have to take classes.
Classes, yeah.
So if you were to just show up and go, it's tandem.
Okay.
It was interesting. You can't really tell you're falling because you're so high.
Yes.
It's not like the ground is rushing
Rising
towards
to,
you.
yes,
It's
yes.
more like you're just, you can't even tell.
It's just
It's
windy.
not moving.
Yes, yeah,
It
yeah.
stays the same and
Yeah.
it's just windy.
Yeah,
And a
yeah.
great view.
Yeah, the great view, yeah.
Yeah.
So that's very interesting. And we'll talk a little bit about that kind of thing. So very, very good. Okay. Okay, so let's start reviewing things. So let's look. Do I have a pen? I do have a pen. So what we can say is that projectile motion, an object that is fired by some means, a cannon or something like that, a spring gun, and then continues in motion by its own inertia. So it's not got a rocket engine on it. The thing that fired it is finished with. Once you're just coasting along like a cannonball, once it's left the cannon, you're continuing by your own inertia, and that's called a projectile. So a rocket is not a projectile. It's got an engine on it, and the engine is firing. So the rocket is not a projectile while the engine is firing. Once the engine stops firing, it becomes a projectile, but not while the engine is firing. The motion of a projectile can be simplified by thinking about a horizontal bit of it, the horizontal component, and its vertical component. And that might seem complicated. My students in Physics 1, they have to do math based on those two things. And components tend to involve trigonometry, and that gets, it challenges you a little bit. So, but it actually does, everything in physics makes life easier. So by using components, it makes life easier. And what are we going to do with it? We're going to kind of appreciate the components rather than getting too involved in them. So we say if a projectile is launched horizontally, so here's the projectile launcher, and it fires it horizontally. So the first thing you say is, well, what would happen without gravity? And the thing would travel at a constant speed, and after 1 second it would be there, and after 2 seconds it would be there, and after 3 seconds it would be there. And that's the horizontal component bit. No force horizontally. Remember, you've left the gun. So all that firing's over with. You're just coasting sideways, and if there was no gravity, you'd keep on coasting sideways. But there is gravity vertically. And so what happens with gravity, it starts pulling you down faster and faster and faster. So you go further and further every second. So after 1 second, you've fallen down by that little bit. And after 2 seconds, you've fallen down by a bigger step. And after 3 seconds, you've fallen down by an even bigger step. So when you put those two motions together, side by side, we see that you've followed, we call that a parabola. It's a special shape. It's a part of an ellipse, actually, but it's a parabola. Very characteristic. Notice that you fall farther and farther every second. My wife was married. I'm her second husband. She was married before she met me. Got divorced, actually. So when I went for my citizenship, I got my green card by myself because of immigration. I didn't know my wife at the time. And then I was a green card holder for probably 30 years. And then when my daughter was born and with changes, I decided it was probably time to get my citizenship. So I went for my citizenship. And for the first time ever, they said, can you prove that your wife was divorced? And I said, well, I don't know. I've never asked her about it. So I had to go home and say, hey, will you give me your divorce papers? Why do you want my divorce papers? Don't you believe I'm divorced? Well, the immigration people, why did they want it? It's like, so, but she was married before, and then she was divorced, and and I actually met the guy. I should stop this. So anyway, she told me this story about how he had this thing about his parents would say don't do something, so he'd do it. So the guy climbed up the biggest oak tree in the back of his yard, and he got higher and higher, and Mum came out and said, you got to stop doing this, and he's climbing higher and higher, and then he heard the branch kind of. He didn't fall, he was still hanging on because there was that little tendril that was hanging on there, but he knew he was going down. And I said, how high was the tree? And she said, I don't know, but he said on the way down, he said, this is really going to hurt. So if you think how long that was, it was about 80 feet. He fell, he broke his legs. It was a real issue. So he had that amount of time to think about it. So he traveled quite a distance. In your first second, you fall by 15 feet. Okay, about 3 meters. In your second, you fall by, I think it's like 125. You can work out the numbers. So anyway, okay, so fair enough. What happens when we fire this thing at an angle? And this is like the wonderful thing about the conceptual physics is it's the same. So now the component is like in that direction, and we're going at a constant speed in the absence of gravity. So I start off and I'd go there, and I'd go there, and I'd go there. And then I fall away from that. So the amount I fell on this other one is the same amount I fell, and the amount I fell by the second is the same amount of falling, and the amount I fell by the third second is the same amount of falling. So the pattern just follows itself. And even if I fire this thing downwards, again, I go this nice linear bit, and then I fall by the same amount as I did the first time, and I fall by the same amount I fall the second time. So it's just like the same pattern, just in a different direction. So it actually makes, and I must confess, I've taught the calculus-based and the algebra-based version of projectiles a lot. And you get used to doing it in the math, and then you see diagrams like this, and you realize, oh, it's just like hanging off a straight line. And I never thought of it like that. It's just like you want to go in a straight line, but gravity makes you not go in a straight line. And your deviation from that straight line is the same amount. Just the straight line might be horizontal or upwards or downwards. But the deviation from that line is the same amount in every pattern. So it's kind of an interesting way of looking at it. So next thing, watching the velocity components. So if I kick a football or throw a ball or fire a cannonball, because there's no force horizontally, there's no acceleration horizontally, and the same speed happens horizontally throughout. So my sideways speed doesn't change because of gravity. But my vertical speed changes by a lot. Initially it starts pointing upwards, and it's reduced by gravity, so I'm going slower upwards, and then I stop going upwards. And then I even start coming downwards, and I have an even bigger speed coming downwards. So At any point, I can combine these two and get my true speed. So we say there is no force component in the x direction, so no acceleration component in the x direction, so velocity in the x direction is constant. The force of gravity acts in the y direction, so there is a constant downwards acceleration in the y direction. Constant force means constant acceleration. So the velocity in the y direction becomes steadily more negative. It changes, becoming more and more negative. In the absence of air resistance, the range, that's how far you go downfield, the range of the projectile depends upon the muzzle angle to the horizontal. It's the angle of elevation. So if you take your gun and you hold it relatively parallel to the ground, you won't go very far because you're going to go a little bit up and a little bit down, and you're very quickly going to stop. If you actually go nearly vertical, you'll be in the air for a long time, but you won't go very far because you're going to go up and then stop and come down. So ironically, you can get to the same range with two paths. You can fire shallow and go there really quick, or you can fire steep and go there really slowly. But you go to the same distance. And I think you use that in sports sometimes. You could lob a tennis ball to the back of the court, and your opponent has time to run back and hit it. Or you can fire the tennis ball to the back of the court, in which case, passing shot, in which case your opponent does not have time to get back and hit it. So two different strategies, two different directions for the same speed, same muzzle speed. So that raises the question of if a shallow angle has the same effect as a big angle, then is there an optimum? And there is. And the optimum is when you trade the two off at 45 degrees. At 45 degrees, you go furthest. So we say, in the absence of air resistance, the range of the projectile depends upon the muzzle's angle of elevation. The greatest range is angle of elevation of 45 degrees. We get similar range above 45 and below 45. The longer time will be above 45. The shorter time will be below 45. Same climb time as fall time in all cases, and equal speeds at equal heights in all cases. So let's take this red line. It's going to take me half the time to get to the top and half the time to come back down again because of symmetry, because there's no air resistance. And if I take any particular height, then my speed at that height going up is the same as my speed at that height coming down. So there's a fair amount of symmetry in this thing. And by symmetry, I mean that 10 degrees above the horizontal, so an angle of elevation of 10 degrees, will behave like an angle of elevation of, what do you think? What big angle will give me the same effect as a shallow angle of 10 degrees? Think about symmetries. It's going to be 80, isn't it? Because it's 10 degrees from the horizontal, like 10 degrees from the vertical. 20 degrees from the horizontal is like 20 degrees from the vertical. 45 degrees from the horizontal is like 45 degrees from the vertical. So that's why there's that one unique point. Cool.
Say like the first part of that again.
So 10 degrees above the horizontal behaves like 10 degrees below the vertical. 20 degrees above is like 20 degrees from. 30 degrees above, 30 degrees from. 45 degrees above is clearly like 45 degrees from because it's the same direction. So just symmetries, in the absence of air resistance. Okay, so that's firing projectiles. What about satellites? Well, first of all, how do we get a satellite? And this is very good. And Galileo worked this out. This is like so cool. You go to the top of a tower and you jump off. And you time how long it takes you to hit the ground. And it takes you basically 5 meters, 15 feet, 1 second. So let's work with that. So it takes you 1 second to hit the ground. let's say that rather than jumping off, you run and jump off. You go horizontally. Well, in that 1 second, you go that far sideways. Let's say you run faster. In that 1 second, you go that distance sideways. Let's say you go faster. In that 1 second, you go that distance sideways. And if you run fast enough, you go far enough sideways that you've got to start taking into account the curvature of the Earth. So if you run even faster, that's how far you go sideways, but the Earth's not there anymore. It's a little bit below. So you go even further. You get this extra boost because the Earth's curving away from you. So if you go further, you get to the stage where in that 1 second where you have fallen by 3 meters, you've gone so far sideways that the Earth has curved 3 meters below the horizon. So you're still as high as when you started. And if you go again, in that 1 second, when you're going to fall another 3 meters, the Earth will have curved another 3 meters away from you. And you go again, and in that 3rd second, when you're going to fall by another 3 meters, the Earth will also curve by another 3 meters.
So you'll just stay in the air.
So you stay in the air. You're falling forever. It's a nightmare. You're falling forever, but you're not getting any closer to the ground. And it's not because you're floating, it's because the Earth is curving. So what gets you into orbit is not upward speed, but sideways speed. And if you think, it's so sad that we don't have the space shuttle, I must confess. But one night I was coming back from socializing, and I had a 4th floor apartment, and I was walking external staircase. I was walking on the external staircase, and I heard this noise, and I looked over, and actually I didn't hear the noise. That's me misremembering. It must have. You can't hear the noise, but something in the corner of my eye caught my eye, and I looked across, and I could see the space shuttle actually on its flight all the way from Tampa to Orlando. It was quite high, and because it was quite high, it was actually traveling more at not even at 45 degrees. It was more like horizontal. It was going north, and it was quite shallow angle that it was going at, as it seemed to me. And that's because it's the game in the space shuttle is not to get fast and high. It's to get sideways and fast. That's what it's trying to do. It would stay at 15 feet, except that the air resistance is so great you can't ignore it, and it would burn the space shuttle up. So they go 100 miles into the air, not 100 miles above the Earth, not to get away from gravity, but to get away from the atmosphere. That's what they're trying to do. So we say that a projectile fired at 5 meter tall tower. Have I been saying 3 meters? No. 5 meters. I've been saying 3 meters, but 15 feet, and that's not right. 5 meter tall tower is 15 feet. So a projectile fired at 5 meter tall tower with a horizontal speed of 1,000 meters per second will travel 1,000 meters downrange before striking the ground. The fact that we have to consider the curvature of the Earth, and this can extend the range. The fact is that we have to consider the curvature of the Earth. The ground curves below the horizontal. So if the projectile starts 5 meters above the ground and travels sufficiently fast, then in 1 second it can reach a point where the Earth is curved 5 meters below the horizontal. So it's still 5 meters above the ground. And this is exactly what a satellite does. We just go fast enough sideways. Turns out you want to do that near the surface of the Earth. I mean, near the surface of the Earth, you need to go at 8,000 meters per second, which, if you're interested, is 18,000 miles an hour. So that's very fast. It's very, very fast, 18,000 miles an hour. Here's the interesting thing, though, which we're going to get to. As you go higher, think about the curvature of these circles. Think of their curviness. Which is the curviest? Is it A? Is it B? Or is it C? Let's put a little thing on this. So if you think A is curviest, assuming you can see that, I'm sorry. If you think A is curviest, click in A. If you think B is curviest, click in B. If you think C is curviest, click in C. So let's have a look. So these circles, a small circle, a big circle, a biggest circle. Which is curviest? Which has the biggest curve? I'm going to stop it in a minute. It's like, I'm going to stop it, and I'm going to say, what did people say? Most people are saying A is the curviest. And I'd agree with that because it's a circle that has a very small radius. And as the radius gets bigger, I can imagine a whole bunch of circles all starting with the same edge, if you like. And I can see that as the circle gets bigger, the amount of curviness gets less and less and less. Yep.
The Earth feels flat.
So the Earth feels flat because it's so big. So here's the interesting thing. If the name of the game is to go fast enough sideways so that in that 1 second the body is curved away from you by the amount that you fall, it turns out that because when you go further out into space you're on a bigger circle, it's less curvy, so you don't have to travel as fast. So ironically, this 18,000 miles an hour is for something in near-Earth orbit, but if you go higher, it gets slower. We have to go so fast because we're near the Earth, and it's really curvy. But if you went out as far as the moon, it would be 27 days to go around once. So you don't have to go about 1 kilometer per hour. It's not the same. So we might talk about that. So we say when a satellite has a circular orbit, gravity does not change its speed. It doesn't speed up or it doesn't slow down. This is because the satellite is moving perpendicular to the direction of the force of gravity. So if I'm traveling that direction, that's my V, and my force of gravity, my Fg is there, then it's not going to speed the V up or slow the V down. But if my V was like that and my force of gravity was there, that would slow down my object. And that's what we see when we throw a ball in the air. The V is upwards and the force is downwards and it slows down. If I had my V going down and my force going down, I would speed up. But when you're at 90 degrees to it, you neither speed up nor slow down. You just change direction. And that's circular motion. So this is because the satellite is moving perpendicular to the direction of the force of gravity. For near-Earth orbit, this happens when the horizontal speed satellite is 8,000 meters per second. When this speed and size of the orbit take 90 minutes, if you work out how big the Earth is, and you work out how fast you are traveling at, you're going to go around once every 90 minutes, and there's no way to avoid that. If you kind of like, you fly over my house and you want to take a picture of me in the backyard, but I'm not there yet, you can't slow down to kind of catch me a few seconds later. You're going to have to go around one more time. So all spy satellites, the ones that take photographs of, factories and bridges and all that, they're all in near-Earth orbit so that they can get good resolution pictures. They all have to do this 90-minute trajectory, and they actually even coil around the Earth, so you have to wait for it to get over the target that you're looking at. Not that I'm trying to change you into spy satellite drivers, but you can't slow down, you can't speed up and stay in the circular orbit. If the satellite is in a circular orbit at a greater radii, then the orbital speed is less and the period of the orbit is greater, so you go slow. Your period gets longer as you go further out, and your speed actually gets less. So it's kind of interesting. There's a thing called geosynchronous orbit, and it is a very specific distance from the Earth. We're 1 Earth radii away from the center of the Earth, and geosynchronous orbit is at 5.5 Earth radii, because when you're at that distance from the center of the Earth, then it takes you 24 hours to go around once. So if you're going round once every 24 hours, and the Earth is spinning once every 24 hours, if you line things up right, you stay over my house. So you can look all the time. It's The resolution of the picture is not as good. So for photographs, it's not so good. But for communications, it's great. And that's what DirecTV uses, and that's what things like the GPS use. They have geosynchronous orbits. There's a ton of satellites at that orbit because it's a very useful orbit to be in. I remember when I got my DirecTV years and years ago, I thought, this is never going to work. You have to screw this little dish onto your roof, and then you point it at the satellite. Where the heck's the satellite? I have no idea. And the instructions said, you know, go to 15 degrees to the west of something and up by 32 degrees. And I look at the little scale, and I'm going, this is worse than a protractor. This is never going to work. And I tilt it, and then it says, connect to your TV set. Oh, great. So I connect to my TV set, and boom, there's a signal. It's not perfect, but it's close. And then it says, just adjust this and watch this little needle go up and down. So I pull on the little thing, and the little needle goes up and down. It's aligned. And I thought, I just aligned a little dish on the roof of my house with an object which is 5.5 Earth radii away from me, over in that direction. And it's there all the time. It was the most amazing, from a science point of view, it was just a really eerie feeling to be able to do that so easily, you know. But it was very easy to do. So I spent the next 30 days watching television because I was on summer break from teaching high school. And then after 30 days, I disconnected it and I gave it away because I realized it was going to be the end of life as I knew it, because I spent literally all my time. I got up and I watched television. I went to bed. I got up and I watched television and I went to bed. So for me, cable TV's a great waste of time. So geosynchronous orbit is really useful. A satellite orbiting at 5.5 Earth radii has a tangential velocity, that's the sideways speed, of not 8,000 kilometers, but 3,400 kilometers, 3,400 meters per second. So it's slower. And if you go further, the moon is about, I think it's about 60 Earth radii away. I think that's where that is. It's a long distance. And it turns out that that is 1,000 meters per second. So we started off near Earth is 8,000 meters per second, and the moon is at 1,000 meters per second. So it slows down the further away you go. If you want to stay in that circular orbit, you better have that speed. What happens if you fire your rocket engines by accident and you stop having that speed? You stop going in a circle. You might stay in orbit, but you stop going in a circular orbit. So we call these elliptical orbits. If a near-Earth satellite sideways speed is too small for its altitude, it follows a parabolic path into the surface of the Earth. When I throw, I'm not going to throw my phone, but this is a near-Earth satellite. It is not going to have the correct sideways speed for its altitude, and it follows an elliptical path around the center of the Earth. The bit that I can see is a parabola. So it's a satellite, it's just not got the right speed. It's just something we throw. So a parabola is part of an ellipse. So a softball really follows an elliptical path about the center of the Earth. Just that the Earth gets in the way. So it doesn't seem that striking, but we're doing the same thing that a comet's doing, just we don't have the right speed. A near-Earth satellite that has the appropriate sideways speed for its altitude follows a circular path. A circle is a special case of an ellipse. And something happened. Let me put that on pause, not now. That's ominous. So we're back, and there was just the light on the monitor went out. So basically, a near-Earth satellite that has too big a sideways speed for its altitude follows an elliptical path. They're all following elliptical paths. The speed of the satellite is not constant during its orbit. And what happens is it kind of overshoots. It goes higher. And and then comes back round. So in this case, the ellipse ran me into the Earth, and in this other case, the ellipse took me beyond the Earth. And that's what, with regard to the sun, that's what a comet does. It follows. Now, let's just think about energy for a little while. When I'm way out here, think about how much potential energy it has compared with when it's down here. Remember that the upwards is in all directions from the planet. It's not up the page or down the page. It's away from the Earth. So if I look at that altitude versus that altitude, what can you tell me about the potential energy at this point? Is it high or is it low? This is very high. And the potential energy here is very low. Yeah? Now, remembering that mechanical energy is always conserved, what can you tell me about the kinetic energy at that point?
Low.
It's going to be low, isn't it? So here the kinetic energy is high. So what can you tell me about the speed at this point? If the kinetic energy is low, what's the speed going to be?
Lower.
So V is low, and here the V is high. So this is what happens with comets. Comets disappear for a long, long time. Halley's Comet, 87 years. Most people get to see it once in their lifetime. I was too busy to bother looking, and so I missed it. And then by the time I kind of took life a bit more seriously and said, I wish I'd seen Halley's Comet, I'm going to be an incredibly old person if I ever see it. So my brother saw it, and he tells me every time he sees me, I remember when I was looking at Halley's Comet. I go, oh man, be quiet, So you guys have a chance to see it, so find out when it comes. It's every 87 years, and look up, and remember me when you look up, okay? So, but we don't see it for 87 years. We don't see it actually for probably more than a couple of months, because it spends most of its time out in a thing called it's the Kuiper belt, the Kuiper, man, I'm forgetting how to pronounce it, the Kuiper belt, and it spends most of its time going very slowly out there, and then it starts whipping round, and it's only a few months where it's visible in this bit. Now this is the sun. I'm changing my diagram. It's only a few months when this is visible. So because it goes very quickly near the sun, and that's when we see it. So it's kind of interesting. So I don't know what you feel, but I'm just like amazed that throwing a baseball is just like Halley's Comet, just like the parameters are changed slightly, but it's the same principle. So along came Kepler. So in the history of things, there was a guy called Copernicus, and he was a cleric. He was back in the 400 odd years ago. There was a tradition of, especially for families that were relatively well-to-do, of what you do with your second oldest child or your daughters. The eldest child would tend to inherit everything. They didn't want the inheritance to be diluted by more and more kids. So the idea was, look, we'll just make the eldest son gets everything, so my estate stays together. And my second oldest son, well, he can sort something out. My daughters, they can marry, it's a terrible system. If you read Jane Austen, if you read the Jane Austen books, that's what they're struggling with. All those women in the Jane Austen books are struggling with this dilemma that they can't own property and they can't inherit. So, and it raises some really, when you see it in a book like that, it really informs you about the reality of those situations. The fact is, you've got a certain standard of living, and you've got to marry to maintain that standard of living. You can't go out and work. You can't work because that's undignified. Okay? So what do second oldest sons do? Well, they join the military. You go and become a sailor or a captain or a soldier. That's okay. Or you join some kind of, in Britain it would be the priesthood. So you join the priesthood. Or you maybe become an academic, but It's something like that. You can't be a business person because trade was looked down on. He's just a shopkeeper, you know. And so an awful lot of people would educate their kids and then push them into something where they could get a living. And I think Copernicus was like that. Copernicus was a cleric, but he was really a scientist. And he kind of like, so he had his duties. He was supported by a parish, and they hardly ever saw him because he was like doing scholarly stuff all the time. He'd do his duties, and then he'd like the rest of the day he'd have to himself. And he was quite an astronomer, and he did not like what was being said about astronomy, because in the absence of true science, people can say whatever they like. At the time, the church, the Roman Catholic Church, said the earth was the center of everything, and if you argued with them, you got into big trouble. And Copernicus certainly didn't believe that. And frankly, provided he kept that to himself, the church had no problem with it. Same with Galileo. Galileo came a bit later. Same, no big deal. Just between us, fine. But don't rock the boat. Because if you rock the boat, then people will stop believing in all of it. So, you know. So it was understood. And Copernicus even sent round some letters to friends saying, hey, you know, the earth is not the center of everything. The sun is the center of everything. And he developed a very nice model for the way the solar system worked. Now, at the time, the scientific community used basically a Ptolemy's model, which was the earth-centered model, which was incredibly complicated. It had been in existence for 1,500 years, and they'd been tinkering it and improving it for 1,500 years. It had the earth at the center, and it had things going in orbit around the earth, but that don't work very well, so they had wheels within wheels within wheels to make the model work. But it did. It could predict the future really well, but it was really complicated. It came to be known that Copernicus was favoring this sun-centered system, and a Protestant crossed the lines. This was during the Reformation. So a Protestant crossed the lines and said to him, look, you got to write this stuff down. I'm too old, I'm too tired. No, I'll help you. So he stuck with him for a couple of years while Copernicus was writing this stuff down. It was a very dangerous thing to do at the time. If he'd been found, he would have been killed. So it was a very dangerous thing to do. And things eventually got too difficult for him. So he said, I got to leave. But the book's almost finished. So he went back to the Protestant countries. And in the meantime, Copernicus and this other assistant finished the job off. And eventually, when Copernicus was really old, the thing was completed. Printing had just been developed. It's like the internet. It's like suddenly we don't need to go to a book publisher. We can write whatever we like and we can put it on the internet. And there's been a revolution of people self-publishing. Well, it was the same for them. They didn't have to get a monk to write this thing down with a pen and ink. They could just send it to the printers and they could print up 100 copies and distribute it. So that's what he wanted to do. He was too old to travel to the printers, so he took it, he gave it to his new assistant. The new assistant, who's young, is going to the printers to print a book which goes against the Catholic Church, which has the power in the country where he lives. And this guy's on this journey, and he's going, hold on, Copernicus is not going to last that much longer. And if I'm not careful, neither will I. So what he did was he put a page in his book, the front page, which said, this is not real. This is just a mathematical model, which is simpler than the Ptolemy model, which is the correct version. So, hey, don't blame it. It's not me, it's math, you know. So Copernicus actually saw that and was outraged because it was real for him. And the guy basically, I think, I don't know, it's not recorded, but I can imagine the guy saying, that's all right for you to say, but, I'm 30, I got another 30 years to live with this. So Copernicus died, and the sense is that Copernicus had the right model and he escaped punishment because he died. The fact is that his model had a mistake in it. He assumed circular orbits for the planets around the sun. And it turns out they're nearly circular, but they're not precisely circular. And so when you use his model to calculate the future, it's awful. So people said, yeah, this is a new model. It's terrible. It gives awful predictions. This is a waste of time. So it wasn't that he died before they could get to him. It was, in fact, that it was no threat. It was like, yeah, you can believe that if you want, but look at the numbers. These are terrible. If this is such a good model, why are the numbers so bad? So it's very interesting. Now, along comes Galileo, who looks at the moon and sees that it's not perfect, which is the church said it was perfect. And he looks at the moons of Jupiter and he sees that they are orbiting Jupiter and everything was supposed to be orbiting the Earth. And then he looks at Venus and he sees a full phase of Venus. And the only way you can get a full phase of Venus is if everything goes around the sun. So he knew that the Earth was not the center of everything. And he published it, and his arguments were good, so he got in trouble. You get in trouble when you do something significant. You don't get into trouble when you do something that nobody cares about, So he got into trouble. He got a house arrest for 10 years. In the meantime, there's other astronomers like Kepler, Brahe. And Brahe is a traditional astronomer. He doesn't use a telescope. He measures the angle between planets and stars. He's trying to build a better and better table. And why do you think that these astronomers are trying, why do you think they're so fixated by where the sun is and where the moon is and where the planets are compared with the stars, and why do they want to know the pattern in the future? Why do they care? What do you think? It is vitally important because they need to improve the astronomy so they can improve the astrology. Galileo himself taught medical students astronomy so they can then cast horoscopes for their patients to decide, is this a good time to operate or a bad time to operate? Astrology and astronomy were very closely linked until about probably 150 years ago. Now, I think quite rightly so, we all say, you will have a nice restful period in the middle of vacation time, It will be cold in the winter time, It's like, so we tend to take it with a grain of salt, but these guys didn't. But you can't use astrology to decide whether to go to war with your neighbor. And so the astronomers did have a problem because they were casting horoscopes to earn a living, and part of the time they were right and part of the time they were wrong. And often it didn't matter. But every now and then your sponsor, Bill Gates, would turn around and say, should I open up a new factory? And you'd cast a horoscope and say, yes, it's a great time to open up a new factory. And then an earthquake would happen and the factory would be destroyed. And Bill Gates, of those days, would turn around and say, hold on, you're lousy at this. You're fired. And so you'd have to find another patron. So many of these astronomers spent their lives going from patron to patron to patron. They'd be fine until they cast a horoscope that mattered. And then they had a 50-50 chance of being right, They'd be the dinner guest. I'd bring inviting friends over. Oh, and here's my astrologer. And he'd talk, be the entertainment. So they all lived a life like this. Very traditional, He was trying to improve things by measuring angles. So in his life, he had an amazing library of measurements. Because what he wanted to do, he wanted to work out the mathematics behind the solar system. He wanted to work out the equation. So imagine, how many people have been to Disney World and been on the teacup ride? You gotta go. It's like you sit in these little cups and the cups spin as they revolve. And then they turn the lights down. So you kind of vaguely see the other people and they're spinning and you're spinning and they're revolving and you're revolving. And it's very accelerating. You do this kind of swirly patterns. You kind of like, you go like that. And everybody else is doing the same. And imagine you're on one of those cups and you're looking at the lights from these other cups and you're trying to work out the mathematical equation that links those motions. It's like impossible. That's exactly what Kepler was trying to do. That's exactly what Brahe was trying to do. He could never do it. He'd get these assistants. As you get older, they give you assistants. He'd get these assistants, and most of them couldn't do it. And then right towards the end, he got Kepler. And Kepler was like amazing. And he wouldn't give him all the data because then Kepler could go away and do it himself. So he gave him just Mars. And Kepler started working out the mathematics of it. And then, as luck would have it, Brahe died. Kepler got all the library. And it took him about 10 to 15 years, but this is what he came up with. The pattern is that each planet moves in an elliptical orbit with the sun at one focus, not the Earth. The sun is at one focus. So here's an ellipse. I'm very extreme. I've drawn this very extreme. But the sun is at one focus. An ellipse, by the way, has two focuses. And if you tie a piece of string between the two focuses and you put your pencil in there and you just trace it out, you form this shape, this elliptical or cigar shape, oval shape if you like. And it's made because the distance from one focus to the point to the other focus is a constant. That's an ellipse. So all planets, got to stop in a minute, all planets follow this elliptical path. How fast does it go? It is a line from the sun to the planet, sweeps out an equal area of space in equal time. So when you're far away, you have a long, skinny triangle and you move really slowly. And when you're nearby, you have a short, squat triangle and you move quite quickly. So that makes sense. And then he even went for, this is the bit that took him the longer bit, he even got the mathematical equation for it, which is that the period squared, how long it takes you to go around the sun squared, is equal to a constant times the radius cubed. Well, radius implies circle, so it's the semi-major axis measurement. It's the average radius, if you like. We can live with that. Let me just see. How am I doing for time? I just don't want to run over. So I've got 7 minutes. So, all right. So if we think about, a bit too far. Okay. So I'm going to, yes. The next thing is if we take the satellite that has a constant amount of mechanical energy because there's no friction, so it's a constant amount. All times during its orbit, then mechanical energy is constant, so the sum of PE and KE is constant. And if we've got a circular orbit, then we have a constant height and we have a constant speed. Constant height means constant potential energy. Constant mechanical energy and constant potential energy means constant kinetic energy, and constant kinetic energy means constant speed. So constant height means constant speed. If you're in an elliptical orbit, when you're low, you go fast because you have a little bit of potential and a lot of kinetic. And when you're high, you go slow because you've got a lot of potential, so a little bit kinetic. So we know that from kinetic energy. So that's where that is. What I'm going to do is I'm going to stop this.